All right. So I think this is, this is homework 8. And it's only one problem. I should have put more in there. But I'll do this and then run over into the next group. I don't know what the next group is. I mean, obviously it must be 9. And obviously I need to be putting more problems out there. But these are already frozen, so. So here we go. Here's the problem. Let's see. It is not that. Oops. Okay, first I got to go back. I'm pretty sure he's going to want to know, determine the pressure at A if the velocity is ejected from B at 0.78 meters per second, 0.78. Okay, let's see what else he has as far as increment. The assembly is mounted vertically as shown like that. Determine the pressure if it is ejected from the, okay. Pressure at A would be back here. He should use an extra word. That is that there are no losses. Maybe I'll address that in a minute. So if it's ejecting at, okay, let me make sure I got the right. B. And he's throwing out at B. That means this. So velocity of B is equal to 0.78 meters per second. Now, the other thing is, I'm going to assume that this is a circular cross section. So this will be a diameter, and this will be a diameter. It makes sense that it would be because you can have square pipes, but you don't see them that much. So that means this is why I don't like letters as far as reference points. AB times VB is equal to AA VA. Too many letters. I'd rather see a 1 and a 2, but that's okay. So the area at B is pi times 0.2 squared over 4. VB is equal to pi times point, that thing, 0.08 squared over 4 times VA. So I'm going to do this, and then say 0.2 squared divided by 0.08 squared VB, but I know VB, 0.78, should be equal to VA. I think that thing can calculate that. I don't know that. Uh, 487 meter per second. Okay, let's think about this. Okay, so let me do this. 200 over 80 squared. 2. All right, let's do this. Since it doesn't matter, let's do it this way. 200 over 80 squared times 0.78. Oh, it didn't pick up the point. Okay. Okay, let's do like this. I'm gonna do this off both of them. Like that doesn't make any good sense. Okay. 4.875. Let me do it off this other one with a parentheses on it. See if it figures that out. Because sometimes it just okay. Let's say 0.8. Yeah, that's that would have been string. So now that I've got that, I've got 0.78 over here, 4.875 over here. Now I got that. I'm gonna take this stuff and move it kind of to the right. Put a big green box around it. Say continuity. And then go back to this thing. So I'm going to set myself up at the thing again. Pressure, elevation, and velocity. Location A and location B. This is my little diagram I like to do all the time. It's not perfectly organized, but pressure at A, 0. I'm going to take this as the datum. So that means the elevation of A. I'm sorry, that's B. B is 0. The elevation of A is that. Elevation of B, 1.2. Now, velocity of A is 4.875. And velocity of O, I got that in the wrong place again. Oops. Yeah, we'll try this. Let's see what happens. There. That's A. And this one was 0.78. So the only thing I don't have is this. I'm going to basically talk about the no losses in a second. 1.2 meters of height is, somewhere around 4 feet. 80 millimeters is small. So technically there could be some losses in here, frictional losses. And the frictional losses come from an interesting place. So this is addition. I mean, I could work the problem and be done with it in a minute. But you have a pipe that's going down here. We saw somewhere back there, the velocity profile could look like this. And generally will look something like that. We also saw from chapter 1 that this was the shear stress. In other words, you take this thing and you take a tangent to it. And if the tangent, like here, at this point, no shear. But near the wall, it has a lot of shear. So this means if you took the fluid and considered it in a free body diagram, looking like that, the pipe is slowing it down with a friction, all while it's flowing. And so essentially, there's a frictional force, and as we knew from dynamics, that frictional force, F dot D, it becomes a minus because water's flowing this way. The shear, if you take a particle of water, it goes from here down to here. But as it's going down that distance, you have this going in the opposite direction. So this shear is taking energy out. So in fact, he should have addressed that. He should have just used the words that said, assume or envisage slow flow or no losses. That should have been a wording that got put in there. And that's actually a pretty important. So the shear stress is what's going to cause this this loss of energy through that pipe. So I'm gonna talk about that in a second after I get done how it's dealt with, but that's another chapter ahead of us. But there's no reason to not include that now. So we're going to go from point A to point B. And what we're going to do is pressure plus gamma Z plus rho V squared over 2 is equal to pressure plus gamma Z plus rho V squared over 2. And this is from location A to location B. But in here should be a term minus losses. But we'll determine that in, I don't know if it's chapter 8 or 9 in this book, but it's not chapter 8 or 9. So it's in one of those two chapters. We talk about and how to quantify this loss. And there's a very organized way of doing that. But right now, we're assuming that there's no energy loss between A and B. It's a good first step to do that, to consider no losses. But then, if you really want to get down to the fine part of the matter, you'll have to include the losses. So what I'm going to do is pluck these straight out of here. And we'll pluck these straight out of here. And I'm starting with the left one. So I don't know pressure A plus. I do know that A sits right here. So it has no, you can put gamma times 0 plus rho 4.875 squared, a lot of energy there. I'll say minus losses is equal to the pressure at B, which is 0, plus the gamma times 1.2, and then plus rho times 0.78 squared over 2. Now I'm going to address what is rho and what is gamma, but before I do that, I got to make sure it's water. Okay, there's the word water right there. So for water, generally, and this is SI units, generally it's thought to be this, unless the temperature increases. But since he didn't give me a temperature of anything, I'm just going to do that. And gamma is equal to rho times G. And since G is 9.81, it's 9810 newtons per meter to the cube. So this is generally thought of, if you don't have a temperature, this is generally thought of as what you should use. So with that, I get this plus, and I don't have to include it here, 1,000 times 4.875 squared over 2 minus no losses. So we'll just say they're gone. And then we'll go back here. And we'll just say is equal to gamma times 1.2, 9810 times 1.2 plus 1,000.78 squared over 2. And now you move that to the other side, 9810 1.2 plus 1,000 over 2 times 0.78 squared, and then I'm just taking that minus 4.875 squared. Let's see. We'll do it like this. Let's see what happens. See if it can read and understand that whole thing. I don't know what it will be able to do. I'm not going to be able to see it all. Okay. Give me a minute, I'm going to stare at it. think it's okay. You get 193.38, and that's in newtons per meter squared that I wrote to the third, or pascals, or whatever you want to call it. So essentially, the first thing is, I mean, this is the thing I think that helps, and I've seen in the past helps a lot of people, and that is this little box. In the past, I've heard people say that's helped them a lot. Actually, put that box down and realize that there are three terms in the Bernoulli's equation. And it is true there's a gamma, but really, if you look at it, the terms you're basically dealing with is the velocity, the elevation, and the pressure. That's it. The others are the two in a row. Those don't mean much. I don't understand it half the time. So if you go in and do that, that's helpful. The other thing I would be a little suspect to is you got to really recognize that you're ignoring the losses. With a thin pipe and 4 feet, they're actually, and that's a fairly, if you think about it, 4 meters, 5 meters, 15 feet in a given second. So 1001, 1002, that's moving the water from here to the door in 1 second. That's pretty fast. In a thin pipe, there's going to be a significant amount of loss. So then the question is, what would happen if you actually had a term here that would say, I'm just going to make it up. I'm going to say we lost. It's going to be in pressure units. So I'm going to just say we lost 10. So we got a minus 10. So if you think about it, you know, this minus 10 would sit here. Let me do it in a different color. You have this minus 10 sitting right here. And then you would move that minus to the other side and it would become a plus 10. So what would happen to the pressure there? The pressure at A would have to jump up, have to increase to overcome the losses that you're going through. So, you know, in limiting thought process, your first thought is, okay, if in fact that was 0.78, you know, if this were true, this absolutely would be true, no matter what. The losses are not going to affect continuity. That being the case, the pressure is the only thing that gets affected. So in fact, this is going to be atmospheric no matter what. So to get this to happen, the minimal pressure is going to have to be this 193. If you start putting up losses, pretty soon you may find this, there may be cases in where this might even double or even triple. So this is the lower limit. So it's good to realize this is the lower limit. If that's the lower limit, then you gotta, if you're going to be using a pump and you can't, and you tune it to getting 193, don't expect that flow rate to be met coming out here. It's going to be significantly lower here than would be if you're ignoring those losses. But if it was a real short pipe and really big diameter, it'd be fine. You know, ignoring those would be fine. So it turns out, let's see, was this the only, let me just double check. Yeah, this was the only one here. I don't know what that means. Hey, wait a minute. What? Okay. This goes away. Then I go back here. Then I go back here. And then I go to 9. Okay, so we'll talk about momentum next time, but I want to finish up the discussion here by actually going, to Give me a second. Oh, here it is. Let's go to E-test. I want to see. Okay, we'll do momentum. Then after that, the sequence should be momentum. And then we should just do a dimensional analysis and then the pipe flow where we get losses. So let me make sure the book is aligned that way. Okay. Okay, so what we got, working energy of moving fluids. Okay, so down in there, there's Bernoulli's equation. So we go down through here, energy equation, that's all good. We're all happy. Momentum. Okay, differential fluid flow, that's going to be fairly short, maybe 30 minutes, and that's it. This one sets us up for this one. Okay, and these two usually are combined into one chapter, but they're not here, but I'll go through both of those. This one's fairly quick, and it's kind of an interesting discussion, but it's kind of historical, but it's also important because fluid flow follows this pretty well. The thing is in mechanics of material, everything was linear, so you could use superposition. Everything would be fine. Nobody really was unhappy about it. You didn't pay attention to anything. Fluids is almost all nonlinear. So you can't really use superposition. So you get stuck in this thing. How do I do this? How do I do this? It wasn't by human design, but it was by humans that actually figured out that you could scale things. In other words, you could take a scale of a jet aircraft, 747, 57, 60, or 777, the big giant one. You can make it, shrink it down, put it in a wind tunnel, and then make it go a different speed, and it would be equivalent to that 740 or 777 going a different speed. And the results match. So it wasn't one of those things that, they were supposing that this would be the case early on. When I'm saying that, back probably around the 30s, maybe even before that. And then it wasn't until they put it in and started doing experiments they realized, oh, okay, it does work. We analyzed this. We thought this was going to happen. It did happen. We were lucky because it happened, because now we can scale things. You can take a scale rendition of something. You can put a different fluid in it. You can put run it differently. The only problems I've ever seen in fluid mechanics deal with ocean-going vehicles, because you'll have a viscous drag because of viscosity, and then you'll have a wave drag, and you can't scale them both the same way. They don't scale. And they could, if someone found a working fluid that would scale perfectly. What I mean by that is you're in your boat in the water out here, and you're wanting to take a scale version, and maybe you could put it in some other fluid, like alcohol or something, that the properties of the fluid would scale, and then the boat side would scale, and you'd get that, but you don't get that. So what you get is there's a thing called a Freud number and a Reynolds number, and it turns out they don't exactly match, and it's hard, but they have figured out a way around this, how they scale their boats, they run them down there, they do certain things to, there's an extra complication when you're talking about ocean-going vehicles. Then you get into waves and stuff like that. That even gets more complicated. When I say waves, there are two ways I'm saying this. One is the boat creates the wave, and that, as in calm waters, and because of that, it creates drag. But then the other is you're going through a rough seas. And so I guess if you move your wrist around, she's probably listening to me all the time. She would probably get some entertaining conversations, but I'm sure I don't really talk about controversial things unless Monty Python and things like that are controversial, but maybe they are. I don't know. So anyway, this is where, okay, let's see. Let me just give us a preview. Okay, okay. So as we go through here, oh, you know, that's the thing. I don't like the fact that you've got to switch. Okay, so let's see. This was in, okay, come on. Where's my mouse? There it is. Oh, it did expand it. That's really strange. So expanded it out. So it started with laminar, okay, Navier-Stokes, laminar flow between parallel plates. An example. So what you see here, I'm sort of jumping ahead. What you see is, okay, so he's got a case where some sort of fluid goes and it goes through these plates. And it turns out you'll get a velocity profile through the plate. Oh, I hope he draws it. Don't tell me you're not going to draw it. Oh, man. Well, let me look at example 2. That's the important part, is to draw it, to have people see that. Okay. Let's see if we draw it here. Okay. May not draw it there as well. Well, how about, I'm not sure. If he didn't draw it in those first two, I'm not holding out much hope. But let's look at steady laminar flow within a smooth pipe. Now, everybody should draw this. This should be drawn no matter what, because this is kind of a standard. Okay, so it does a free body diagram on it. And he's talking about the outside, the shear on the outside of the slug of fluid that's slowing it down. And there we go. There's the velocity profile. So that velocity profile, the derivative of that is proportional to the shear stress, using the viscosity as the constant of proportionality. Turns out a more viscous fluid with that same profile will produce more shear stress on the wall, and as a result, a little bit more losses. So you get down through this, and he'll have the shear stress distribution for laminar and turbulent flow for this. And then, let me see if I can, there's somewhere down here. Okay, here he has an equation for the velocity as a function, and this one is a pipe, so it's the radius. So in fact, if R is equal to R being the big R being the outer rim, or not the rim, but near the wall, then those two become nothing there. And so here he has the there's the maximum velocity. And that's funny, that looks like a video of the previous section. So it turns out he comes up with something like this. Now, if you stare at this for a minute, this is kind of interesting. So the change in pressure is proportional to, it uses the proportionality to the viscosity. But if you don't have that, then let me do it like this. Let me phrase it like this, because I can probably do a better description if I can get this on the page. As a matter of fact, I'll just grab all this because I might be able to read those things. They look kind of small, but I can just use the bottom of it. So he says like this, right? You know, so Q is equal to AV. So if he wanted, so he's sitting there saying, here's what he's actually saying. Consider this to be like a straw you put in your mouth. You put high pressure here and low pressure down here, you're going to get velocity coming out of here. Let's write Bernoulli's equation between those. P without, I'm going to label this 1 and this 2. P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. Now, if you're just doing Bernoulli and you're including no losses, continuity tells you that these two velocities are the same. And the elevation of this pipe is such that it's the same. So as a result, the pressures are the same. So Bernoulli's by itself tells you that if you took a piece of pipe, you laid it on the ground, had the same pressure on both ends, air would flow straight through it. That's not possible. It's not going to happen. So then there's a faultiness here. So how do you handle this? So what you do, let's see if I can kind of move this. I've kind of goofed up. So here, let me do like this. Try to get some of these scratches out of here. So I can get the equation. There we go. So I'll take the thing and slide it over. And now I got to produce, I'm just going to put an L for right now. So we know everything cancels out. And then we'll say P1 minus P2 is equal to some L. But we don't know what the L is. But let's assume it's laminar flow, because that's what this equation came, that's where this equation came from. So this L is some number or some equation. But if we look at back here and we say, hey, well, we got viscous thing, we're basically looking at this. There's your delta P. So this is nothing more than delta P is equal to, let me see if I can, I shouldn't have used, how I'll do like this. This is what I'm saying. It's a funny new symbol. LOS, LOS. I didn't realize I should have, because there's an L right there. So if you take this thing and monkey around with it, this equation tells you that, let me see if I can get this. Okay, so I'll take the Q, the 128, the mu, then I'll have to put the L up here, and I'll put the pi and the d to the fourth, is that right? So I'll go ahead and do this, and I'll say AV. So it makes sense, okay? And think about this. If I have, okay, let's take the limiting case. And the limiting case is one in which logic tells you it's not even consideration. It equals 0 in this equation if mu is equal to 0. If there's no losses. Okay, the other thing is, it would equal 0 in here if there was no velocity. That makes sense. So it turns out in this case, if you think about it, and I'll go back to this, and the reason I'm going back to this is something interesting. So if you look at this and you say, okay, let me write my numbers, 128 mu L over pi d to the fourth, and I'm going to take the Q. So now I'm going to do something very bizarre. Remember this equation? But I'm going to reverse these two and put R and then I. So V equal IR in a circuit. This is a current or a flow. This is a flow of, that's a flow of electrons moving down a wire. This is a flow of fluid particles moving down a wire. This is a force, this is an electrical force making it happen. This is some sort of pressure force making it happen. So this is nothing more than the resistance. It turns out for laminar flow that it is linear. It turns out, here's the difference between if you drew a circuit, delta V and current, and they have this beautiful thing like that, and the slope is the resistance. In fluids, it does like this. Oops. Well, it can't do it. It's got to do, it's linear for a while, and then it becomes quadratic up here. So circuits actually are that same way. But you don't talk about that because most of the circuitry in like this computer and my cell phone is driven to such a low current. You don't want to have high current there, because if you have high current, you actually do have this. And then things become nonlinear. But if you have a high current in this stuff, things catch on fire and blow up. And so they don't want to design up here. Now, in fluids, we don't have that luxury because everything that happens up here in the nonlinear plane. Matter of fact, if you're designing a fluid circuit to move around in the laminar region, nobody's going to be happy because the flow is moving so slow it can't transfer much energy. So you want it to go fast. Circuits is the other way. So circuits exist in this. We touch upon it, but in fact we move to something more complicated, and that's kind of, so that's to tell you what losses, where they're coming from, and then he should go. Okay, so there you go. So he went on to that. But if you take the Q and move it off to the right, you'll see the 128 mu L over pi d to the fourth is like a resistance. I mean, that's all it really is. Okay, now I got to figure out. Okay, so now, okay, did I touch it? Okay, I did. So he says within a smooth pipe, I guess this is a good way to do it. Oh, look at all that. It's telling me. So it's kind of the same thing he did before. Okay, now he's coming up with the whole Navier-Stokes equation. Here's what's so funny. I mean, that's just kind of a side point. You got a velocity times the velocity and derivative. This is the nonlinear component in these parentheses. On the right-hand side, it's all linear. Turns out if you have any sort of velocity movement, you're going to get the nonlinearity. So you can't avoid it. And that, complicates things drastically, that convection term. But you can ignore it, which is what he's done here. You ignore it to begin with because for laminar flow, you can ignore that. Then what happens? Okay, go. You have to do it 2 or 3 times. Or you have to be patient. It turns out there's a number called a Reynolds number. Okay, so this is actually an experiment we've got in the lab. It doesn't look exactly like this, but it is pretty much like this. We've got a little metal tube that sits in there in this long clear pipe, and you can watch, if you're in laminar flow, you get that ink just kind of going down there. And then you pick up speed and it starts transition. You can see it sort of swirling around, and then poof, you can see it just. Now, in the experiment, what happens is it comes in red, and it doesn't say the same darkness. It sort of dissipates or becomes more opaque because you got that red dye that occupied that amount. It becomes from dark red to kind of a light shade of red. So it doesn't become this dark. But this is I guess if you had, I don't know, if you had something that you could do in the dark, take a picture in the dark and had the right kind of lighting, you probably might see that. But there's that experiment that exists in our lab. And then he's starting to talk about, okay, so here's the key. This is pretty accurate. So if the Reynolds number is less than 2300, generally it's laminar flow. But if you back that out, you'll find the velocity isn't moving much at all. As a matter of fact, it's really hard to get water to flow slow enough to be laminar. It's just almost always turbulent, or at the very least, it's in transition. So so what happens is there's a set of equations. Let's see. And okay, so apparently it's in chapter 10. Resistance to flow in rough pipes. I'm looking for a thing called a Moody diagram, which I hope he describes it as doing that. But where might it sit? Pipe, but it's got to be before pipe systems. It has to be. Maybe it's in this one. Resistance flow to rough pipe. Okay. Now I have really confused it. Okay. Okay, let's see what we get out of here. Okay. Now that's really. So here he's talking about the Moody diagram. Now the value of it is at the top of the Moody's diagram. But where is the Moody? I wonder if it's in the last chapter. And I just missed it. Anyway, that's the where you. I'm gonna have to wait till I get there. If you go and find, you can do this. Here, I'll just search for it. It's in this book somewhere. It has to be. This is, I mean, you can see how standard it is. Look, there's that, there they all are. And if I wanted to view all, you're not going to see them look much difference at all, except maybe that one they put more description on it. Look, this one they color coded it, but you can see the look. They're all are exactly the same. Here, this one, oh, this one's saying it's PDF. Look, to me, it looks like the Wiki Common one looks the best. And so what you get is there's the Reynolds number, the roughness of the pipe, and then what's called the friction factor. This is what you use to get the losses. And we'll go through plenty of these so you can, because this is very important if you're starting to take your PE or FE exam. This is, I mean, this is expected. You're not expected to memorize this. You're expected to, if you're given this in the pipe system, you know, what is the pressure? If you're blowing through a straw and out's coming a certain speed, or you're able to produce a certain pressure in your mouth, how fast, what's the speed coming out of the air of the straw? And you'd use this Moody diagram to get to that. So we'll do several problems like that. So, I mean, that's a description that, I mean, I've gone kind of over the top on this, but the fact that he did not describe no losses is not deeply concerning to me, because I don't think I get concerned that much about stuff anymore. But it is something that should be stated in each of these problems when you're doing it. Now I've lost where I was. I was there. I was looking at the assignments. I was on week 7? Or maybe I was on 8. On 8? That's 5. It couldn't have been. I was on it. That's week 8. It's in week 9. It's in week 9. Okay, minimum. Okay. So what we'll do is we'll pick back up on this, and then I'll work a couple of problems related to this thing. Yeah, that's a complete description with lots of stuff on it for your enjoyment. See what the thing looks like in the... I don't know how you can stick all this. This has got to be in the above view. Or maybe it's to the left. It's to the left. Wow. Okay, so it's all crammed in that little space right there. So we'll come back and do this one next time. It's crammed all in that space. There's a lot crammed in that space too, but the equations actually looked okay. And I don't think I can move this from left to right. I think I'm just stuck. I can make it bigger, but that just makes it so I can see it. Doesn't really, but the equation fit in between the two sides, there and there. So I guess it did okay. It looks okay. Picture looks okay. F stand, exhaust, fuel, oxidizer. So he's probably going to come in. He's going to set this whole thing up. And he's probably going to figure out his Part A. Oh, wait a minute. I think I had it there. He's going to find the the X, the force, if it's steady flow, it looks like you're going to find the force coming out to the right. So you're going to have to find, see it says F stand. So the force in the X direction to hold this so it doesn't go flying around the room. And then the effects of pressure, part B. And then what else? The effects of the exhaust. And that's it. So we'll come back in and do this. Okay, let's see. Consider rocket mounted fluid and oxygen flowing to the rocket engine on the left side with that. And, okay, that's the fuel. That's the oxygen. Pretty high ratio there. The exhaust flows out to the right, standard atmospheric pressure, and temperature is that. Moderately hot. The nozzle diameter is that. The diameters of the inlet are this and that, and the gauge pressure at the propellant lines. Where's the propellant line? Oh. Okay. The gauge pressure in the propellant lines, I'm guessing it has to be both of these lines. And the densities are that and that. The flow of the propellant through the engine will generate a force on the rocket to the left. Okay. This force called the thrust element. The test stand must generate an equal opposite force to hold the engine stationary. But does he tell me? Oh, he does. The exit. Okay. Does he tell me the diameter at the exit? He calls that DE. This is going to take a little picking around to kind of find all the numbers out of all this. Let me go back up to A. Does he give me any extra information here on A? No, not really. But where's DA? Okay. Because they got to have that. I'm sorry, DE. DE. Oh, there it is. It's 60. Okay. The diameter is the inlet. The gauge pressure, propellant line. Yes, densities. The fuel. The densities are fuel. Now, wait a minute. Rho of the fuel and the gauge pressure of the propellant line and the densities are. So I'm assuming that that is related to the oxygen and this is related to the fuel. Flow of propellant through the engine will generate force. This is true. So this will be an interesting problem. Okay, so we'll do this one. Okay, so here's the effects of the propellant flow. You will want to know, let's see. No, wait a minute. He doesn't put a thing right here. Isn't there supposed to be like a symbol, F stand or something? He doesn't do that here either, unless me shrinking and making it grow has messed it up. Let me push the F5. Oh. Uh-oh. That wasn't what I wanted to have happen. Uh-oh. Where did it go? Oh. How do I refresh it? How about reloading it? See if there's a little... Ooh. Oh, no, it didn't. Okay. Using the entire rocket engine. Calculate the momentum flow due to these two terms. Which two terms? Okay, the horizontal portion. Using the entire rocket engine as a control volume. There are two open control surfaces for the propellant inlets. Oh, so you just want to know the components there. Now, the momentum equation is similar to the force on surface and what is the force on the control volume due to these pressures? Okay, so you have a pressure here pressure here. Let's force to act in the right to be positive. Okay, then what's the effect of the exhaust? The increase in the momentum flux is created by the energy extracted from combustion. What is the momentum flow out of the control volume due to the exhaust flow? So you want to know the momentum here. Does he sum them all up? No, he does not. So you never really sum them up. You just do them in little parts, which I guess that's okay. You just got to read the words. This looks a lot like what you would see on the FE exam. Something where there was a lot of information and you would immediately work to find the F stand, but he's asked you something simpler in part A. And so it's this concept of reading the question. So, I went over my time. Yeah, that's what I was planning to do.